Hey everyone. What I want to do in this video is go through a few examples of how trigonometry is commonly used when working with vectors, and specifically in how we describe vectors. Now, a vector is any quantity that has both a magnitude and a direction, and we often represent that with an arrow. It has a certain length and it's pointing in a certain direction. And let's say we've also chosen some sort of coordinate system, so some Cartesian coordinate system, or we've already chosen what the x direction is and the y direction. When we describe this vector, there's two very common ways that we use to describe the vector. We can talk about it in terms of its length, the magnitude of that vector, and some direction. This is the Greek letter theta, it's an angle that we're given. Or we can talk about this in terms of how far does this vector extend in the x direction and how far does it extend in the y direction. We'd refer to that as the components of this vector. Now you'll notice that this shape makes a nice little right angle triangle. And trigonometry gives us the tools such that if I'm given, for a right angle triangle, if I'm given two of the sides, or if I'm given one side and one of these two angles, we can completely reconstruct the entirety of the triangle by using different aspects of trigonometry. So that's where it's going to be very, very useful in also dealing with vectors, because again, sometimes we're going to want to talk about the vector in terms of its magnitude and direction. Sometimes we're going to want to talk about that vector in terms of its components. And again, trigonometry gives us a tool to change between these two ways of describing the system. Now, when we're dealing with these triangles, if we're looking at a particular angle, we give different names for the different sides of the triangle. The hypotenuse is always going to be the longest side of that right angle triangle. It's going to be on the farthest point from the right angle of that triangle. The opposite side is the side that is furthest away from the angle that we are interested in. Okay. And the adjacent side is the side that is also connected to that, the vertice that is we're looking at with that particular angle, but it's not the longest side of the triangle. So we do need to be careful, because let's say I were to draw a triangle in this way. So that's my given angle, and that's the right angle. Then this side would be the hypotenuse. This side that is furthest away from that angle, that would be the opposite side. And this other side would be the adjacent side. So we do need to be careful when we're drawing these diagrams to make sure we're properly labeling what's the hypotenuse, what's the opposite side, and what's the adjacent side. Another thing that is incredibly important, you need to make sure that whatever calculator you're using, it's in the correct mode. If you're using angles that are given in degrees, you want to make sure that your calculator is in the degrees mode. And you can check this by plugging in sine of 90 degrees should give you 1. If you are using angles in degrees and you type in sine of 90 degrees and it gives you anything other than 1, you're going to have to look up for your particular brand of calculator how to change that mode to degrees mode. If you're working with angles in radians, well, then sine of pi over 2 should be equal to 1. For the purposes of this video, I'm just going to be using angles in degrees for this one. So if you're following along with this, make sure that your calculator is in degrees mode right now. Now, some of the common equations that we're going to be using with trigonometry, well, first we have the Pythagoras Theorem, which says that the hypotenuse squared is equal to the length of the adjacent side squared plus the length of the opposite side squared. You may have also heard this as a squared plus b squared equals c squared. So we're going to be using that Pythagoras Theorem. And these are the different trigonometric functions that we're going to be looking at. The sine of whatever angle we're using, that's going to be the ratio of the opposite side over the hypotenuse. Cosine of this angle is the adjacent side divided by the hypotenuse, and the tangent of that angle is the opposite side over the adjacent side. So basically, these trigonometric functions, you can kind of think of them as machines where if you give that machine an angle, that machine will output the ratio of two of the other sides of the triangle, two sides of the triangle. So let's look at some examples of how we can use these trig functions in different cases. So let's say I have a triangle, and let's say that this side length of the triangle is 17 meters, and let's say that this angle is, I don't know, let's say 64 degrees. And suppose I want to figure out what are the other two sides of the triangle. Well, first off, we should make sure that we've identified which sides of the triangle we're looking at in each part. So the longest side of the triangle, that's going to be our hypotenuse. The side of the triangle that is furthest away from this angle, that's going to be our opposite side. And the remaining side, that's going to be our adjacent side. Let's start by figuring out what is the opposite side of this triangle. So notice we have the angle, 64 degrees. We're trying to find the opposite side, and we have the hypotenuse. So we need to identify which of these trig functions is going to be most useful for us. We want to make sure it includes the thing that we're solving for, and the only other things that it includes are things that we have values for. So notice if we look at this sine function, we have the angle, we have the hypotenuse, all we're looking for is the opposite side. So let's write down that equation. Well, we can start subbing in some values because we know that the angle that we're looking at is the 64 degrees. We don't know the opposite side, so let's just leave that as opposite, but our hypotenuse was 17 meters. Now, if we're trying to solve for the opposite side, we can rearrange this equation to solve for it. So let's multiply both sides by 17 meters. So we'll get 17 meters times the sine of 64 degrees is equal to the opposite side. And now we're at a point where we can plug this into our calculators. So if we do 17 times the sine of 64, I get 15.28. So 15.28, the meters still follows, we keep those units. That's equal to the opposite side of this triangle. So that's going to be 15.28 meters. Okay, so we have that opposite side of the triangle. What if I want the adjacent side as well? Well, we're trying to find the adjacent side. We've got the angle, and we have the hypotenuse, so let's try our cosine function, because again, we want to pick the trig function that includes the thing that we're trying to solve for, and all of the other things are things that are known. So we're trying to find the adjacent side, we know the angle, we know the hypotenuse. So we can do the same thing. Cosine of 64 degrees is equal to the adjacent side over 17 meters. And we're trying to solve for the adjacent side, so let's multiply both sides by 17 meters. And now this is something that we can just plug into our calculator. So 17 times the cosine of 64, I got 7.45 meters for that. 7.45 meters, that's our adjacent side. 7.45 meters. So from only having the hypotenuse and that angle, we can figure out what the opposite and adjacent side lengths are. And a good check to do, whenever you finish one of these questions and have that diagram, it's a good thing to kind of check to make sure your answers make reasonable sense. For example, in this case, that angle that we were using, that 64 degrees, 45 degrees would be directly diagonal. It would be the same distance horizontally as it is vertically. So those two sides would be the same if it was 45 degrees. But this triangle that we're looking at, that angle is 64 degrees. So that's a larger angle, which means there should be a larger vertical part to it than horizontal part. And when we actually check this, yeah, we find that the vertical portion is greater than that horizontal portion. It's a quick check that you can do to make sure that you haven't accidentally mixed up when you're using sines and cosines. I strongly, strongly recommend using your diagram and doing some of these quick checks. Let's look at another case. Suppose we have another triangle where in this case, you were given the adjacent and opposite sides, but now we're trying to find out what the hypotenuse is and what the angle is. So let's say I've got another triangle, And let's say that this one, let's say this side is 57 meters, and this side is 48 meters. And we want to figure out what is the hypotenuse for this, and we want to solve for this angle. Once again, we should probably label each of the sides of this triangle, so we have our hypotenuse. If this is the angle that we're going to be interested in, then the angle on the side, on the far side, that's our opposite side. And we have the adjacent side. So how would we jump into this one? Well, if we have the opposite and adjacent sides and we're trying to find the hypotenuse, if we're trying to find the magnitude of this vector, then we're probably going to use Pythagoras Theorem. So let's write that one out. So we've got hypotenuse squared equals adjacent squared plus opposite squared. And we can start subbing in some numbers. So the adjacent side, that was 57 meters, and we square that, plus 48 meters, and we are squaring that. Okay. And that side of the equation, we can plug that into our calculator. So 57 squared plus 48 squared. I got 5,553. Technically, this would be meters squared right now. And that's the hypotenuse squared. So if I just want the hypotenuse, I need to take the square root of both sides of this equation. So we take the square root of both sides. And I got 74.52. So the hypotenuse, in this case, is 74.52 meters we would be left with. So let's put that on our diagram, 74.52 meters. Excellent. What about this angle? Okay. So if I'm trying to find this angle, we need to, again, use one of our trigonometric functions. And in this case, well, we actually have all three sides of the triangle, so we can use any one of these that we want. I'm going to use the sine function for this one. So let's say sine of that angle is going to be equal to the opposite side over the hypotenuse. And let's sub in some numbers. So we've got 48 meters for the opposite side, and we've got 74.52 meters for the adjacent side. And if I calculate that fraction, 48 divided by 74.52, I get 0.6441. So 0.6441. So this tells us what the sine of this angle should be equal to. But I don't want the sine of the angle, I just want the angle on its own. So how do we do this? Well, if we have an expression like this, where the sine of some angle is just equal to this particular number, to, in a sense, undo a sine function, literally we call it the inverse sine function. Depending on your brand of calculator, you might need to look for this button. The inverse sine function, it sometimes is written like this, so sine with a little -1 on the top corner there, or sometimes this is written as arc sine. These mean the same thing. But when I have an expression like this, if I take the inverse sine of both sides of this expression, well, if I take the inverse sine of the sine of this angle, that will just give me back the original angle. And on the other side, we're going to have to put in the inverse sine of 0.6441. And this, again, is something that you can plug into your calculator. You might have to check to make sure you know where that inverse sine button is. Very often on calculators, there will be a second function button. So it's like second function sine, plug in the number, and then that'll take the inverse sine. But if I take the inverse sine of 0.6441, in this case, I get basically 40.10 degrees. 40.10 degrees. So in this case, if I'm given the two sides, the adjacent and the opposite side of this triangle, I can use Pythagoras Theorem to find the hypotenuse. and I can use some of these inverse trigonometric functions to figure out what the angle is. Okay? And I encourage you to try solving for that angle, say using the cosine and eventually having to take the inverse cosine or take the inverse tangent. Try some of those different methods on your own to make sure that you're able to use different versions of those trig functions to reach the same conclusion. Now, before we submit this as our kind of final answer, it is still good to take a quick check to see if this number is reasonable. Notice in this triangle, the horizontal component is a little bit larger than the vertical component of that triangle. Not much, but a little bit more in the horizontal direction. So again, if I think of a vector as an arrow pointing in a certain direction, and those two horizontal and vertical components of it, this angle has to be such that it's pointing more in the horizontal direction than it is in the vertical direction. Okay? I said before that 45-degree angles would mean it's going the same distance in the horizontal as it is in the vertical, which means that in order to get this angle to go more in the horizontal direction, that angle has to be less than 45 degrees. And when we look at what we actually got, yes, it does match up that that angle is less than 45 degrees. And we know that automatically because we're saying this triangle is extending more in the horizontal direction than it is in the vertical direction. So it's still a good idea to make these kinds of checks and make sure that you're on the right track and that you haven't accidentally, again, flipped when you're looking at sines or cosines or mixing up some of these trigonometric identities. So the last thing that I want to mention about this is we can use this for any other kind of vector. So let me back up here for a moment. So in the previous questions, we said, let's imagine I've got a triangle where this hypotenuse is 17 meters, and we're looking at how far we extend in the horizontal direction and how far we extend in the vertical direction. Going back to our original picture of vectors, this is the same thing as if I have a particular vector and a coordinate system, so an x and a y coordinate system, or it could be north-south going up and down and east-west going to the right and to the left. And suppose that this angle was, again, 64 degrees. And instead of this being a distance of 17 meters, let's say I had a car that was driving at 17 meters per second in this particular direction. So an object moving in a particular direction. Instead of this being a position vector, we're now looking at a velocity vector. But if I want to find the horizontal component and the vertical component of this velocity vector, we use exactly the same tools that we had when applying trigonometry to this literal triangle. We can use the sine function to figure out that, the vertical component of this is going to be 15.28 meters per second. And this horizontal component, we can use the cosine function and rearrange that to find out that in the horizontal direction, it's moving at 7.45 meters per second. Again, this could be something like a projectile. I think I started with a car, but cars aren't going to be driving vertically. The point is that for these velocity vectors, we can break them up into components in the same way that we've taken this triangle and looked at those different side lengths. Or instead of this being a velocity vector, maybe it's a force vector. So maybe instead of these being velocities in meters per second, maybe this is a force in newtons. So there's a 17 Newton force pushing in a certain direction. We'd use exactly the same tools to figure out, this is how much the force is pushing horizontally, and this is how much the force is pushing vertically. Keeping those units associated with that as units of newtons for a force. Same thing with if I have the x and y components of a vector and I want to find the magnitude and direction. If this was, let's say, let's go with a force vector again. Let's say there's 57 newtons of force pushing to the right and 48 newtons of force pushing vertically. Well, the magnitude of that force vector overall would be 74.52 newtons pushing in a direction of 40.1 degrees above the x-axis. We can use these tools in exactly the same way, and that shows up a lot in not only intro physics courses, but any kind of question where you're dealing with vector quantities. So we'll call that good for now. I have a couple of examples on here. There are numerical solutions posted in the description. Again, one of these is looking at a force vector where I have a force pushing in a certain direction. The only thing we'd have to be extra careful about in cases like this is if I have a vector that's pointing in a different quadrant, we're going to have to be careful of whether, let's say, the x component is positive or negative. And similarly, whether the y component is going to be positive or negative. How we interpret the positive or negative signs is going to depend on which component we're looking at and which quadrant that vector is actually pointing in. Another question is, again, same kind of question, but this one we're talking about magnetic fields and saying how strong is the magnetic field in microtesla. Don't worry about the units of that. It's just the units that we sometimes use for measuring magnetic fields. But if I know the x and y components of that magnetic field in these units, can I find the magnitude and the direction? Again, solutions will be in the comments for that, but we'll call that good for now. As always, if you have questions, throw those into the comments, and have a good rest of your day.